in this recording, we're going to discuss gas exchange. So before we can start talking about how oxygen and carbon dioxide move and why, we need to talk about the behavior of gases. So we have two laws. We have Dalton's law and we have Henry's law that help us understand why gas exchange occurs in the way that it does. Okay, why oxygen comes in, why carbon dioxide goes out. The first is Dalton's law of partial pressure. Okay. So we've talked about air being a mixture of different gases. It's not just oxygen. Okay, it's actually not even majority oxygen. It's majority nitrogen. Each gas that we find in the atmosphere, in the air that we breathe, each of those gases exerts its own pressure. We call this a partial pressure, which is where this big P comes from. So we've got these, okay, I told you these big P's weren't just typos. Okay, so these big P's represent partial pressure. Each gas individually, okay, exerts partial pressure. So all of the gases in the air that we breathe, okay, if we add all those up, that's where we get our total pressure from. We know this total pressure as your atmospheric pressure that we've been mentioning, that's 760 millimeters of mercury at sea level. So the three main components of the air that we breathe are nitrogen, oxygen, and argon. Okay, there are a few others. It's such a small percentage that they just kind of get left out here. But by and large, the majority of the air that we breathe in is actually nitrogen. It's actually about 78% nitrogen. Okay, oxygen makes up about 21% by volume, and then argon is not even a full percent. Okay, and again, we've got other gases and things in there as well. This would equal 100%. Now, each of those, okay, so our partial pressure of nitrogen, if air is 78% nitrogen and our overall pressure is 760 millimeters of mercury, then nitrogen's partial pressure would be 593 millimeters of mercury, and so forth and so on for the other two as well. Okay, so these are the partial pressures. So why do we care? Okay, we care because the partial pressure of a gas, okay, within the air that we breathe, determines where the gas will diffuse. Okay, so you are already familiar with diffusion. You know that with diffusion, things move from a high to a low concentration. Okay. The rate of gas diffusion, moving from a high pressure to a low pressure, right? Because diffusion, high to low, right? Now it's just pressure. The rate of diffusion, so how quickly the gas diffuses, is determined by the steepness of the pressure gradient itself. So the greater the difference, okay, in a partial pressure outside of the body versus inside of the body helps the gas move faster, diffuse faster. Okay, so this is one of the reasons that oxygen moves from outside of our body to inside of our bodies, while carbon dioxide moves from inside of our bodies to outside of our bodies. Okay. Now, here we go. All right, Henry's law. Okay, so Henry's law has to do with how well gases dissolve in liquids. Okay, and why do we care? Well, because remember how where are we going to put all this stuff? Ultimately, we have to do exchange with the blood, which is liquid, right? So, how well a gas dissolves in liquid is based on both its partial pressure and its solubility. And solubility is really just, does it dissolve or does it not? Okay, or how well does it dissolve? So, nitrogen. Okay, we just said that by volume, okay, air that we breathe is by volume 78% nitrogen. So it has a very high partial pressure. Okay. However, little nitrogen is found in your blood plasma because nitrogen is not very soluble in water. And you know your blood plasma is mostly water. Okay. So you don't find a whole lot of nitrogen, okay, dissolved in your blood plasma, because you physically can't really get it to dissolve in the blood plasma. Okay. Now oxygen, okay, it has a lower partial pressure compared to nitrogen. Okay, 21% is what we calculated on the last slide. But It is found dissolved somewhat in blood plasma because it is more soluble in water compared to nitrogen. Okay. Now, these are really just relative comparisons. Okay, so nitrogen is not very soluble, so you don't have very little to no nitrogen in your plasma. Oxygen is a little more soluble than nitrogen, so you find a little more oxygen in your blood plasma compared to nitrogen. Okay, carbon dioxide, which has the lowest partial pressure between these three gases. Okay, in fact, we didn't even mention carbon dioxide on the last slide. It's less than 1% of air that we breathe by volume. Okay, but it is also found dissolved in blood plasma because its solubility is 20 times greater than oxygen. Ooh, yeah, 20 times greater. Okay, so what do we think that means? Hopefully we think that means that you are going to find a ton of carbon dioxide in your blood plasma, which is exactly how it's going to work. You're such a genius. I'm so proud. Okay, so we are going to look at this beautiful picture. We've got a couple gases over here. We're going to focus on oxygen and carbon dioxide because, gas exchange. This is just the percent of by volume of the composition of air. So we said that air is by volume 78% nitrogen, 20% oxygen, yada yada. Okay. This next one is the partial pressure at sea level, okay, of these substances. Okay, and again, we're going to focus on oxygen and carbon dioxide. So at sea level, okay, outside of your body, okay, so the air that you're breathing in when you're in your backyard, okay, oxygen has a partial pressure of 159, okay, carbon dioxide has 0.3 millimeters mercury, okay. Then we're going to move to the partial pressure in the lungs, okay, and the blood in the lungs. And then we're going to move to the partial pressure of your arterial blood gas, ABG. Okay, so what is floating around in your blood, okay, in your arteries. And then we're going to move to the partial pressure in your cells. Okay, so that's what's happening. We're going from outside of your body to your lungs and the pulmonary capillaries to the your arteries, okay, into your cells. Okay. So let's trace oxygen. Okay, outside of the body at sea level, oxygen has a partial pressure of 159. Okay, it's very high. Again, do not go home and memorize 159 versus what, like, we're watching trends. We're looking at trends. Okay, so outside the body, 159. Okay, lungs and in the pulmonary capillaries, we're down to 104. Arterial blood is down to about 80 to 100. Inside the cells is 40. Okay. Where are we moving? How are we moving? We're moving from high to low. Coincidentally, isn't that how diffusion works? Yes, nod your head yes. Okay, we're going from high to low. Okay. These partial pressures, okay, are helping drive oxygen from outside of our body all the way into our cells, which is very nice of it. Okay, and we do have our little side note down here. If our partial pressure of oxygen in our arterial blood drops below about 60, we do consider that to be hypoxic. You're going to need to get you a little oxygen tank. Okay, now carbon dioxide, okay, outside your body, 0.3. That's pretty low. 0.3, y'all, not even 1. All right, 0.3. Okay. Notice a little bit higher in the lungs and pulmonary capillaries, a little bit higher in your arterial. I keep saying arterioles, your arteries too. Okay. 45 in your cells. So it's kind of high in your cells. Coincidentally, which way is our arrow going? Ooh, bloop. Okay. Carbon dioxide a higher partial pressure in your cells compared to outside of your body. magically, carbon dioxide moves from your cells to outside your body. Again, these partial pressures are helping assist with moving oxygen from outside to inside our bodies and moving carbon dioxide from inside of our bodies to outside of our bodies. Okay? Now, we do also have additional values for carbon dioxide here. These two actually will be good to know. Okay? If you have partial pressure of less than about 35 of carbon dioxide in your arterial blood, we consider that to be an alkalosis. So your blood pH has gotten too high. If we have greater than 45 millimeters of mercury for carbon dioxide in your arterial blood, we consider that to be acidosis. So your blood pH gets too low. Okay, carbon dioxide directly affects the pH of your blood. Okay, so having too much or too little carbon dioxide can result in alkalosis or acidosis. We are going to spend a lot of time, okay, on these two conditions. All right, so these are going to come up, but you are going to want to know these two numbers, okay? Not necessarily for right this second, but when we start really talking about acid-base, you're going to want to know these numbers, okay? Okay, so we learned all that just so we can learn about gas exchange, okay? Pulmonary ventilation really only brings air into and out of the alveoli. Okay, it's literally just breathing in and breathing out. You actually still have to do gas exchange. So during pulmonary gas exchange, oxygen is going to diffuse from the air in the alveoli, okay, which is coming from the atmosphere. It's going to diffuse into your pulmonary capillaries, and carbon dioxide is going to go the other way. Carbon dioxide is going to move from the capillaries into the alveoli, where we can then later breathe that out. You have two processes involved in gas exchange, because we do pulmonary gas exchange, which is what we just described, exchanging oxygen and carbon dioxide between the alveoli and the blood. And then we have to do tissue gas exchange. So then we take all that oxygen to the tissues and the body cells, drop the oxygen off, and pick up more carbon dioxide at the cells and tissues. So this would then be the tissue gas exchange. Sometimes we refer to pulmonary gas exchange as external respiration. Okay, that would be the diffusion of the gases at the alveoli and the pulmonary capillaries. Again, we are going to convert the oxygen-poor yet carbon dioxide-rich blood. We're bringing that to the lungs. Okay, you know, ultimately we bring all that blood to the lungs through the pulmonary arteries. Okay, and then we do the gas exchange, the pulmonary gas exchange. So we take up all that carbon dioxide back into the lungs. We drop off all of that oxygen into the blood. Okay. When we looked at that table a few minutes ago, that pressure gradient, okay, is what favors the diffusion of carbon dioxide from the capillary blood, okay, into the air, so we can breathe it out. This difference is not as steep, okay, but it is helped by the fact that carbon dioxide has a high solubility in water within the plasma. Okay, so that's assisting in moving the carbon dioxide back out of our body. Okay. The oxygenated blood that has been, we've done gas exchange at the capillaries, we're going to return that to the heart via the pulmonary veins. So then the heart can distribute that well-oxygenated blood to the body, where we can do tissue gas exchange next. Again, in the chart that we looked at, the blood has a low partial pressure of oxygen, okay, compared to the atmospheric partial pressure of oxygen. So that favors diffusion of oxygen into the blood, okay, on its way to the tissues. Okay. And just one more time, we're going to keep pounding it in, y'all. We're going to get it. Okay. So you can see the partial pressures for oxygen. It's higher in the alveoli compared to the capillary. So where do we move? We move from the alveoli into the blood of the capillary. Partial pressure of carbon dioxide is the opposite. It's higher in the capillary compared to the alveoli. So how do we move? We move from the blood in the capillary into the alveoli. Okay. Same thing. Okay, same thing, just a different way. This kind of shows you how perfusion or gas exchange can be affected by things like an obstruction, okay, or what happens if we bronchodilate and bronchoconstrict, okay. How does that affect gas movement? So take a look at that as well. Now let's do tissue gas exchange. Tissue gas exchange, also known as internal respiration. We're going to exchange the oxygen and carbon dioxide at the tissue and the cell level. We've seen in the chart that the partial pressure of the oxygen and carbon dioxide is what helps drive the directionality of these gases moving. So the cells have the lowest partial pressure of the oxygen, so it's pulling that oxygen into the cells, while the partial pressure of carbon dioxide is largest in the cells, so it's being pulled out of the body basically. Okay, so that's what we got going on there. Okay, so I'm really just saying the same thing 12 million times, but y'all gonna figure it out. Okay, yep, here we go. Oxygen at the tissues. Now this is at the tissues. Okay, so the previous picture was at the lungs, this is at the tissues. So now the partial pressures are driving oxygen from the blood into the tissue, but it's driving carbon dioxide from the tissue back into the blood.